Welcome to the webinar. I'm going to be muting everybody for the webinar so that we don't hear a lot of crosstalk. And once the masterclass is done, we are going to open up for question answers. So I'd really appreciate if you could mute your microphones. That way we don't hear any crosstalk during this webinar. We are going to be recording this webinar, and we are going to be sharing the video later and also the labs. So thank you for making it to the webinar. I know that we have a lot of people from the West Coast, so I'm based out of Boston, and it's 2 o'clock in here. It's a beautiful day in here, and I'm looking forward to talking to you about some of the things we've been doing at QuantUniversity and the recent collaboration we have been having with the CFA San Francisco Society. And I'm also going to be sharing some of the case studies about AI and machine learning. And this one-hour masterclass was delivered at the CFA annual conference in May in London, and it was very well received. And so we have kind of condensed that 1.5-hour masterclass into a 1-hour session. And my goal today is to kind of talk to you about some of the advances which are happening in machine learning and AI, especially in the financial services world, and what a CFA and financial professional would need to know about AI and machine learning. So for people who don't know me, my name is Sri Krishnamurthy. I'm the founder and CEO of QuantUniversity. I've been practicing analytics and machine learning for more than 15 years now. My graduate studies was in machine learning. And when I entered the financial services world, I was fascinated by the confluence of all the data sets we had out there, the time series related data sets, the cross-sectional data sets, the text-related data sets. So most of my career has been working with large data sets and working with challenging problems to see if we can gain insights when we build these analytical solutions, primarily to help decision-making in the financial services world. I'm also an adjunct professor at Northeastern University here in Boston. I've been teaching data science and machine learning for the past 6 years out there. And prior to that, I was at a company called MathWorks, which makes MATLAB. And for more than 5 years, I was leading various financial engineering and machine learning related engagements. My affiliation and association with the CFA Institute goes back to 2007. So I'm kind of very proud, and it's a nugget I always share whenever I interact with CFA charter holders and CFA candidates. I was in the first team which won the global CFA Institute Research Challenge, and I mentored multiple CFA Research Challenge teams. And I really love to kind of interact with the students, and the whole challenge has grown significantly. And whenever it comes to education, I'm very passionate about bringing in some of the insights we've been working in the professional services world into the educational realm. So this particular webinar, when we started talking to the CFA San Francisco Society, so we found that there's a lot of interest in the Bay Area in trying to integrate machine learning, AI, and financial services. And we thought that we're going to create a 1-hour masterclass to introduce some of the concepts of machine learning and AI, and how does it connect to financial services. So let me dive deep into some of the key concepts of AI and machine learning, which some of you may have already been tuned to. You're kind of already listening to various press releases. You've been learning a lot of things from the media. You've been probably practicing it also in your own companies. But today, I want to kind of give you a 60,000-foot view of some of the key trends of AI and machine learning, and what are the key drivers out there. And the next thing I'm going to do is dive deep into what machine learning is all about. My goal is to kind of give you a workflow on typically how do people build machine learning applications. And then I'm going to show you a fully functional case study on how to build a credit risk application using some of the key machine learning and AI principles I'm going to discuss today. Okay, so let's kind of dive deep into some of the key aspects of AI and machine learning. So for people who have been tracking AI and machine learning, we are supposed to be looking at the evolution of how technologies have evolved. And right now, we are in what is called as the fourth industrial revolution. All the things we have been exposed to from a digital sense in the context of the Alexas, the Google Now, the Siri, the innovations in AI, is helping us create decision-making systems which are kind of beyond what we thought which was possible. And machine learning and AI has helped bridge the gap between what humans thought would be feasible in when we're trying to build out automated systems and automation kinds of systems. But today we have the notion of intelligence being built into these systems. So in a few years, we are probably going to see flying vehicles and flying cats. So this was a slide there was a recent article which talked about flying cars and flying helicopters in a crowded area. So it's kind of the Uber in the third dimension, if you will. And today there was a release which the NEC basically tested out a flying car which was 150 kilograms and which could hover over the ground for more than a minute. So we are going to see a lot of these kinds of innovations come into our lives on a daily basis, and finance is not immune to all these innovations. We're going to see a lot more innovations of AI and machine learning in the financial services world. Also, if you want to kind of look at where we are in terms of the state of the art in AI and machine learning, you have to look at the various publications which are out there and various key themes on AI and machine learning, wherein a lot of researchers are spending a lot of time. So this graph, which was, I kind of looked at some of the key trends in the context of publications which talk about where researchers are spending a lot of time and energy on in terms of various technologies, and also the patent filings, which basically tells you how companies are looking at IP in the context of AI and machine learning. So the graph you see on the left is basically a graph which talks about the various scientific publications in the context of AI. And you can see that there's a significant uptick in the number of scientific publications since 2000. And in the last 5 to 7 years, you are seeing a significant number of scientific publications. But you can also track the patent filings have also significantly increased. So if you drill down into some of the key themes and key ideas which researchers are working on, you can see areas like neural networks, support vector machines, rule-based learning, deep learning. All these are key concepts in the context of AI and machine learning, which has got significant attention both in the technical research community, but also in the industrial community, because the number of patents which are being filed in these areas are also significantly increasing. What that means is financial institutions are heavily investing in AI and machine learning related infrastructure, and they're also gearing up with increased demand for the talent in this particular space. So you can see a lot of companies hiring a lot of quants and data scientists and machine learning professionals, either in the context of automating various processes or trying to build an infrastructure to help them make better decisions using AI and machine learning related technologies. Now, I want to kind of give you a quick snapshot of how these things would come into play. So on the left, you see a tweet by Elon Musk. So this was a tweet, exactly a year ago, 7th August 2018, 9:48 a.m. California time. Elon Musk sends out a tweet saying, "I'm considering taking Tesla private at 4:20, funding secure." And this tweet in the East Coast time was at 12:48, and Bloomberg later released a social media post, which basically talked about the price impact which happened the moment Elon Musk sent out a tweet. So this was at 12:48 when Elon Musk sent out this tweet, and it was already in the Bloomberg newsroom headline within half a second or so. And you can see the price impact happening more or less in the next few minutes. And the point here being that information is getting bombarded to us in such a high pace that it's impossible for humans to take decisions based on just humans making decisions alone. So you have to have the machines and the infrastructure to basically take a look at this information and see if there's something important in here which will help you make important decisions. Okay, so let me also talk a little bit about where we are seeing the industry going. Now, if you were trained as a quant, 10, 15 years ago, most likely you would be looking at some of these technologies you see on the left. So you'd be talking about stochastic models, factor models, optimization. Most of the financial engineering classes I took were were in the context of derivative pricing, looking at simulations, distribution fitting. And most of them were statistical in nature. There were a lot of modeling involved, and we had to make a lot of modeling-based assumptions. In the last 5 to 7 years, the field of data science has grown significantly. And most of the things you kind of hear about today are things like machine learning, natural language processing, deep learning, computer vision, graph analytics, sentiment analysis, predictive analytics. Most of these are data-driven. So the paradigm has shifted from looking at primarily from a modeling approach based on assumptions, based on samples, to looking at data-driven approaches wherein you have abundant amount of data and you're looking at all these technologies which are able to kind of figure out what the patterns are in these data sets and build out models to help you make decisions. Now, if you are either in the CFA program or if you have been tracking some of the evolutions of the CFA program, so you now have a reading which talks about fintech and AI, and it's kind of being embedded into the curriculum. So you see that the CFA Institute is also seriously looking at all these innovations and integrating some of these learnings into the curriculum. So why are we talking about AI and machine learning now? So I want to kind of give you 3 major drivers which are significantly impacting the evolution of these technologies in today's world. The first thing is the data. So if you were looking at data 15 to 20 years ago, we had data which could potentially be put in a large server, which could be local in your enterprise. And you had the technologies to basically slice and dice the data, process the data, which was all more or less local. In today's day and age, you have a large volume of data. You're collecting data in very high granularity, and the variety of data which you're collecting is also so huge that it's impossible to basically think about data as something local and something could be stored locally. On the other hand, you're also seeing a lot of time series related data sets which are also collected in increased granularity, and the velocity of the data is also something which you'll have to factor in when you're making decisions. And then there's a lot of uncertain data sets, so you'll have to figure out what data sets are actually something which are of value or things which you'll have to just ignore in the processing of these data sets. So with all these data available, people are now thinking about how do we look at all this data? How do we process all this data? Because it's impossible to bring all these data sets in an environment like Excel or programming tools to kind of work with it. And that's the reason why you have a lot of innovations happening in the software world. On one hand, you have large-scale distributed technologies which are enabling you to process all these data sets in a parallel and distributed computing mode, which will help you make decisions in a distributed way if the data could be processed simultaneously on multiple nodes, including that of the cloud. On the other hand, you're seeing a lot of frameworks leveraging technologies like deep learning, which are heavily used to uncover patterns which are done in ways which was never thought about before. So for example, if you look at technologies like Keras or TensorFlow or Microsoft CNTK or MXNet, most of these technologies have been backed by large companies like Google, Amazon, Microsoft, and they are spending a lot of time and infrastructure and research money to bring about innovations and making it available in an open source world to help you make, to create algorithms, to create infrastructure which can help process a lot of all this information to make decisions. Now, in addition to the data and the various software programming methodologies which are out there, you have a lot of innovations in the context of hardware. On one hand, you have specialized hardware like the NVIDIA supercomputing infrastructure, which helps you make calculations much faster by leveraging GPUs. On the other hand, you can scale these calculations horizontally by leveraging cheap infrastructure, leveraging that on the cloud, which will enable you to scale your calculations without you having to invest on those infrastructure. What that means is the confluence of the data, the smart algorithms, and the hardware are basically enabling you to make these decisions in such a way that you are able to now create various algorithms and frameworks to make decisions in the financial services world much faster and much better decisions. Okay, so that's a little bit about the high-level view of some of the innovations which are happening in the AI and machine learning world. Now, most of these things which I talked to you about are things which you probably had already heard about in the media, by attending conferences and things like that. But what does it take to actually build a machine learning algorithm? When you talk about building a solution internally and thinking about leveraging AI and machine learning within your enterprise, what does it actually mean? Who are the people who are going to be building these solutions? What are the various, who are the various stakeholders? What are their roles and responsibilities going to be? What do they typically do when you talk about AI and machine learning? So when we use these terms, AI and machine learning, we sometimes use them interchangeably. But in the context of when you look at the whole analytical solution suites out there, you have to kind of just segment out these definitions a little bit so that you can contextualize and focus on the right kinds of problems you may be having. For example, if you're looking at artificial intelligence, it's termed as the intelligence demonstrated by machines, but machine learning is just basically a subset of artificial intelligence. So in the context of machine learning, you'll be looking at things like supervised learning, unsupervised learning, reinforcement learning, and deep learning, and things like that. But artificial intelligence could be a combination of some of these machine learning technologies. And in addition to that, it could include also some decision-making rules and other kinds of rule-making systems. On the other hand, you'll also have things like big data analytics, which basically helps you bring the big data and the data perspective when you're doing these kinds of calculations. So how do people typically build out these kinds of solutions? So let's spend a few minutes on trying to understand, who are the people and the stakeholders who are typically involved in building out these machine learning solutions? What is typically involved when you're building out these kinds of solutions? Okay, so let's kind of look at this workflow in a second. So here, what I'm showing you is this entire flow starting from data or ingesting or acquiring data to deploying a machine learning model in production. So typically, when you get in data, it could be data from various websites, it could be data stored in databases, it could be data acquired from various data vendors. So typically, once you get this data, you had to kind of get a feel for the data. How do you explore the data? What kind of data do you have? You may use things like Tableau or Excel or whatever your tool of choice is to understand the nature of the data. And then you may have to think about cleansing and pre-processing the data so that it gets into a form which is actually usable. You may have to do some what is called as feature engineering to understand the most important features which are out there so that you can process those aspects of the data. And typically, most of these tasks are done by who are called as data engineers. So the data engineering task is to kind of understand this entire pipeline of how do we get the data in a form which could actually be used for modeling. Nowadays, what's happening is people are thinking about using what are called as microservices and containers, and they are automating some of these pipelines and enabling reproducible pipelines so that you can automate some of these aspects. And the field of DevOps is what is called as development operations, which is basically enabling people to standardize on certain technologies so that instead of you having people in an ad hoc way processing all these data sets, they basically enable you to kind of build out pipelines which could be automated. That way companies don't have to redo the same processing again and again. Now, typically when you talk about modeling or building machine learning models, you would involve data scientists or quants. And this part of the slide I'm showing you is typically the key steps which are involved in building out models. You start with the data which has been cleaned and processed, and then you have to think about, well, how about we try out different algorithms based on the goal and the problem we have at hand. And I'm going to give you a little more details about some of the algorithms which are out there. But what you typically do is you build out different kinds of models, and then you have to figure out whether these models actually work, and can we tune these models so that they perform optimally. And then you have to think about, well, what are the various choices I have in selecting some of these models, and how do I make these models available in a production setting so that people can actually use these models in the context of useful tools. So the key players involved would be data scientists and quants, who are typically involved in building out these models, and then working with the IT teams or the software engineers to put these models into production, either on a cloud, or it could be through some kind of an API, to enable the analysts and the decision makers to access these models and to make decisions based on these models. So I just wanted to kind of give you under the hood view of what typically happens when you start thinking about building machine learning pipelines in an enterprise setting. And the reason why I wanted to kind of share this was, most of the times people assume that building machine learning models will just involve quants starting out with the Jupyter notebook and just working with the data. And that's true when you start out, when you're building out initial machine learning models, but enterprise adoption would typically involve all these steps and various key stakeholders who are going to be involved in building out different kinds of algorithms. Okay, so now that we have an understanding of what are the various steps involved in building out the machine learning models, let me focus on the key task at hand, which is how do we build a machine learning model from scratch? So I want to kind of share 5 steps which are typically involved when you're building out machine learning models. So I'm going to gravitate, instead of focusing on all the steps, I'm just going to focus on these 3 boxes in here. I want to show you through a case study on how models are typically built, some of the techniques which are used to build out these kinds of models. How do you evaluate whether a model actually works? And how do you typically deploy these models in production? So I'm going to give you a brief introduction to these processes in the next few slides, and then we will switch to a demo, and we will work through some of the details through Jupyter Notebooks and through examples. Now, when I shared the emails with you, so let me just kind of switch the screen for a second. So you should have gotten an email which gave you a link to this Q sandbox page, and this page basically has the slides which I am presenting to. So if you want to follow along, you can just go to the link in here, and you can either download these slides or kind of follow through these slides. I also want to tell you that when we run through the lab, we're going to be running this lab on what's called as the Q sandbox. I'm going to show how to go about starting this and running this when we get there. But I just want to make sure that if you are wanting to try out the lab as we speak, it's a good idea to just basically go about registering on the Q sandbox with the code I've provided to you, so that you can follow along the logs when we get there. Okay, so let me get back to the presentation. So let's start talking about what's involved with building a machine learning model. So if you've never built a machine learning model before, so the first thing you had to think about is, what kind of data am I working with? So typically, if you're working with data, you will, I've just given you a snapshot of an Excel sheet, if you will. So you have various columns, which has various features about the individual records. and you have records, which basically are observations. So for example, if I want to build a credit risk model, each person would have a particular credit profile. They'll have a particular salary. They'll have, a place of residence, family, etc. So those could be individual observations. On the other hand, the attributes or the characteristics of the data would be presented in columns. And once I have this data set, I have to start figuring out what kind of data do I have, how many of these are what are called as categorical data variables, which means that there are either flags like yes or no, do you own or do you rent? So that could potentially be a flag, or it could be numerical information like what is your salary, what's your credit score. So all those could be numerical bits of information. So typically when you're working with data, you have both numerical and categorical information, which you'll have to think about processing as you go. Now, you also have to factor in the kind of data you are working with. For example, you may be working with time series related data sets, wherein the data has to be continuous. So if I'm looking at projecting sales in the future or earnings for the future, I have to leverage the information which I've collected in the past. And so that would typically be in the context of time series related data sets. On the other hand, you may have data which are typically what are called as cross-sectional data sets, which do not have the temporal continuity, which are independent records. And at that point, we do not have to worry about the data being in a continuous way. Okay, so what I basically told you is some of the things we need to worry about in the context of data. You could have either cross-sectional data sets or longitudinal data sets. In the context of cross-sectional data sets, you may have to work with numerical and categorical data sets. Typically, in the context of longitudinal data sets, you'll have numerical data, but you could also have sequence data, but we'll just focus on the numerical data sets. The next thing you do is, once you have your data set, you have to frame your goal on why you are thinking about leveraging machine learning or any other technique. So you have to start framing the question on what is my goal? What am I trying to do in here? So it could be in the context of building out descriptive statistics. I want to explain what has happened in the past. I want to understand my business, how things have gone in the past. I may be looking at various companies and their earnings and the relationships between various businesses, the relationships between how the company operates versus other companies, their performance in various geolocations. All those are typically what are called as descriptive statistics. Typically, no machine learning is involved there. You're trying to use statistical techniques to summarize the data and getting a feel for what has happened in the past. On the other hand, you may have what is called as predictive analytics related problems. And the goal there is, well, now that I understand how things have been working in the past, can I leverage this information to project what may happen in the future? And this is typically forward-looking, and that's where we are thinking about using machine learning and AI techniques. So in the case study I'm going to present, we are going to focus more on the predictive analytics piece rather than using the descriptive statistics piece. Now let's look at some of the predictive analytics or the machine learning problems in closer detail. So when I talk about goals, you have to be able to think about, well, what am I trying to do in here? So for example, I may be having a population and I want to build a model which will segment this population in different classes. I may have a universe of stocks and I may be thinking about clustering these stocks automatically. I may be thinking about, if I do not have any labels in my data, what do I do with this data? Can I segment them into individual buckets and try and understand the characteristics of each of my sub-buckets? So all these are what are called as clustering kinds of problems. And these are typically what are called as unsupervised learning problems because you do not have a label to be associated with. I'll tell you a little more about unsupervised and supervised in a bit. But you have to start thinking about what am I trying to do? Am I trying to segment out the data? Or I may be thinking about predicting something. So an example could be predicting the salaries given work experience, education, etc. So if I give you a couple of different variables, can I predict a new variable? So that could be what's called as a prediction problem. On the other hand, I may be able to predict a class. For example, I'm putting together an application for a loan. I'm providing my FICO scores, the current loans I have, my employment status, and then figuring out whether I'm going to get a loan or not. Am I eligible for a refinance at this point or not, et cetera, et cetera. So those are all problems which could be termed as prediction problems. Now, there are a lot of different methodologies you could potentially use, and typically in a full-fledged class, we go about working through some of these details. But in the context of this masterclass, what we are talking about is, in the context of the goals for predictive analytics, depending on the kind of data sets we are working with, we may either have a segmentation goal or a prediction goal. Now that we know the data, now that we have a goal in mind, we have to then think about what are the various tools and algorithms available which will help us frame these data sets and problems we have in the context of a model. So when you start talking about machine learning models, it's a whole science by itself. Graduate students spend a couple of years in their master's programs learning these techniques. PhD students kind of focus on specific techniques and work on these extensively. There are hundreds of thousands of algorithms in each one of these buckets, enhancements and improvements to each one of these algorithms. But at a high level, if you're looking at machine learning algorithms, you could typically bucket them into 4 buckets. One, what's called as an unsupervised learning problems, wherein there are no labels. Supervised learning problems, which we'll talk a little bit about in the context of case study. And there are 2 other specialized classes. One is what's called as reinforcement learning and semi-supervised learning problems. Now, let's focus on the goals we talked about and talk about the kinds of algorithms which are used to achieve goals in the context of prediction. So if you wanted to get a little bit under the hood and figure out, like, well, let me kind of operate from a modeling perspective. So let's say I have a few variables, let me call them X in here, and I have to model the relationship between my variables X and another variable Y. My goal is to come up with a model which will map the relationship between these X and Y variables. And the simple thing we have to think about is, if this Y is a numerical variable, we call it as a prediction problem. And if this Y is a categorical variable, we call it a classification problem. So for example, if you say that given that a customer's debt to income ratio increases 20%, what are the chances that he would default in 3 months? Could be the problem we are trying to answer. And we could structure the problem in this particular way. Now, the key thing to note in here is we do have historical observations of these X's and the Y's. So if we do not have all the data, we have to think about cleansing the data in here to think about the way in which you can create the data sets which could be used for building out these models. On the other hand, if you do not have Y, there's no point in thinking about a supervised learning problem. You have to either start labeling your data sets and then think about incorporating a supervised learning framework, or you may have to start structuring the problem as an unsupervised learning problem, wherein you do not have any labels, but then the goal would be, based on the observations and the variables you're looking at, I would like to build a model which could potentially classify these observations into multiple buckets. So for example, if I have a list of emerging market stocks, and I do not know which sectors they belong to, and I do not know much about these stocks, I could potentially leverage some of the numerical parameters of these stocks, historical performance, various ratios, etc., and then run a clustering algorithm, and then see if I could bucket them into similar stocks, and then see if characteristics of these stocks would reveal themselves once they've gone through automatic clustering. So what I want to kind of basically tell you is the algorithm choice is not the primary thing. So you start with your data, you start with your goals, and then you think about, well, I have to now pick an algorithm to address the goal in mind, and I have to structure it in the context of either a supervised or an unsupervised learning problem in this particular case. And then the question comes in, well, what kind of algorithms are available? So I want to talk about three algorithms because these are the three algorithms I've used in the case study. One, I'll kind of use what is called as a parametric framework. And the parametric framework is basically, we are trying to build a model which will give us a set of parameters which could be used for prediction. So the simplest one would typically be something like a linear regression. In the context of a linear regression, I'm trying to find an equation y is my intercept plus the coefficient multiplied by x in this particular case, but I can go with a multilinear regression framework wherein there could be multiple x's, if you will. But the point here is I want to understand, based on the best fit I could potentially have, what are the best parameters I could come up with. And you could use ordinary least square regression or any other regression framework to come up with these parameters. You could also think about creating a parametric framework which will go and not only look at the linear relationships, but it could also include some nonlinear relationships, look at relationships in various ways, and build out what's called as a neural network framework, wherein you are trying to understand various weights and biases. And based on the various weights and biases, I'm going to come up with a neural network model which will map multiple inputs to the various outputs. So these are two examples of what are called as parametric models, which will assume some kind of a functional form, and the goal is to fit the coefficients based on the past observations of the various variables. Typically, these are like the independent variables, and trying to understand the relationship between the dependent variable of that. Okay, on the other hand, what you could also do is you could use what are called as non-parametric models, and here you don't have to assume some kind of a functional form. So in this particular case, I used a functional form saying that there is a linear relationship between my y and x's, and that's the reason why I came up with this equation in the first place. But here, you don't have to assume the non-parametric form. And there are various algorithms, for example, what is called as a KNN, or the k-nearest neighbor algorithm, basically looks at a variable and says, well, can I find neighbors which are similar to me? And based on k, which is the number of nearest neighbors, I'm going to affiliate myself with my closest k neighbors. And it's a very simplistic rule, and you can look at various distance metrics to figure out whether you're close to the red triangles in this particular case versus that of the blue squares, and go from there. On the other hand, you can also use what are called as decision rules, and these typically use recursive partitioning. And you come up with these decision rules so that you can automatically split your data. And the goal there is to come up with the best possible decision tree so that when I get a new observation, based on the various decision rules I have, I can label the data. So in the context of prediction, these leaves will have a set of variables, and the average or some kind of an expected value of these leaves, the variables in the leaves would be used as a proxy or the expected value of that particular new record. So for example, if it's about pricing a particular car, it could be the brand of a car, the age of a car, the miles per gallon, et cetera, and then you can end up with the price of a car being that of the leaf. So you may have a lot of similar cars in here, and you take the average of these cars, the price of these cars, to be the price of a particular car. Now, what's happening is a lot of researchers are thinking about, well, why use one decision tree? Because I could potentially have multiple ways in which I could create these decision trees. And that's where what are called as ensemble models are being popular nowadays, wherein you build models that are what are called as random forests. So it's basically a forest of decision trees, wherein you build an ensemble of various trees to build out a model for prediction. Okay, so I'm not going to spend a lot of time explaining all the algorithms which are out there. That's kind of left for a larger duration class. But I just wanted to give you some highlights on when you talk about various algorithms, you have to get to a little more granularity instead of just saying, okay, I need a machine learning algorithm, to figure out like, what's my goal? What am I trying to do in here? What are the various algorithm choices do I have? Do I have any restrictions in the context of parametric versus non-parametric? And then do your algorithm choice. So there are a lot of newer techniques which are being applied I just wanted to give you a context that what we have done is just basically scratch the surface of machine learning. The machine learning researchers and professionals typically do a lot more, apply it in various settings, such as natural language processing, look at various combination of various techniques, which are typically what are called as ensemble learning techniques, look at various ways in which you can tune these models, which are typically what are called as automatic machine learning, and then leverage the nature of the data, typically in the images and videos and things like that, and then use techniques like deep learning for specialized kinds of problems. Okay, so now that we have understood different kinds of algorithms, so now let's talk about the process. So I told you the whole flow chart, but if you look at the whole flow, so you start with ingestion, you cleanse the data, you understand the various features, you have to do a couple more things in the context of machine learning. So when you look at machine learning, you typically say, well, I have all this data. Let me split this data into, let's say, 80-20 split, build the best possible model with my training data, and then figure out whether my model actually works by testing with the data which was never seen by the model in the first place. And if I can get good results with my testing data, then I could say I have a pretty decent model. And the process of tuning basically goes, using cross-validation and various other techniques to understand, what are the best choices of parameters and potentially hyperparameter tuning to get to the best possible results. Now, how do you think about best possible results? And that's where performance evaluation comes in. And what people typically do is they come up with various metrics. And one simple metric is what's called as a mean absolute percentage error, which is to basically say, what's the percentage score of predictions which deviate from that of an average? And I want to use this as a metric to figure out, give me the model which gives me the best or the lowest error rate in this particular case for my particular model. So using that, we can now think about evaluating multiple algorithms so that we can say, well, I'm going to use MAPE as a measure, or root mean square as a measure, or some other metric as a measure, and then compare different algorithms and choose an algorithm which gives me the best possible error rate. Okay, so I know I'm overwhelming you with a lot of details. It's not easy to just, if you're being exposed to machine learning, this may be more of a review, but if you've never been exposed to machine learning, I'm probably giving you a lot of details. But I also want you to appreciate the rigor which goes into machine learning. Machine learning is not just about wearing a creative hat and designing interesting theses and then saying, oh, okay, it works. It involves a lot of engineering. It involves a lot of process. It involves a lot of rigorous ways of understanding the data, getting to know the various possibilities which are out there, tuning, testing, figuring out whether the algorithms actually work, and then consciously making a decision to say that this machine learning algorithm actually works, and we'll have to deploy it in production. If it's not done in the right way, it's just going to be an experiment, and experiments always don't succeed. So sometimes you may get dejected because you do not spend enough time in terms of performance tuning. Sometimes you may not apply the right kinds of techniques. So there's a lot of design of experiments and experimentation done. And there aren't really standard recipes to say, okay, you have to do this particular thing. There's a lot of experimentation which needs to be done. And that's the reason why a lot of emphasis is now being placed on responsible machine learning so that you are looking at rigorously how you can structure these problems and test it out. And education and making sure that people who are knowledgeable about these aspects are being brought in to develop projects so that you can understand the value of these and also do enough testing so that you can, when you deploy these algorithms, you know that they actually generate value and it was not just a fluke, that it actually worked in one case. Okay, so I've given you a lot of information in this particular case. So let's kind of move on to the case study in a bit. So what we're trying to do in here is build a credit risk model and a consumer credit risk model. What I'm going to do is there's an open data set out there on a website called Kaggle, and it's called the Lending Club Loan Data. The Lending Club is basically a peer-to-peer marketplace. So here people can go and say, you know what, I want to buy a boat. The boat is going to cost me $10,000. I want to loan $10,000. I own a house. I earn so much. I have these loan obligations, but I don't want to put it on my credit card. Can someone lend me money? And investors could, go and invest in these notes, and they could potentially fund your loan. So there could be hundreds of people who may say, okay, I'm going to give you $25 or $50, $100. And if the loan gets funded, you'll get an aggregate rate. It could be 16% or 20% or whatever it is, depending on the risk profile of that particular person and the purpose of the loan, et cetera, et cetera. And what Lending Club has done is they've given out many of these actual loan records on their website, so you can download and get actual data. It's not synthetic. You can see the profiles of different people, the various purposes, whether the loan was funded or not, and you can download the data and play with that. And a lot of institutions are actually using it for building different kinds of models, and students love this data set because there's real data sets. They can understand whether the data actually works, the models, do they actually work or not, and then get a better feel for working with real data sets. So I would highly encourage you to try it out. So what I have done is basically created this credit risk pipeline wherein we're going to ingest this Lending Club data, we're going to do some pre-processing and build out a model and show you how it's deployed. So let me just kind of switch screens for a second. So what you're going to see now is basically the credit risk application. So this is the application. If you go to the link I sent you for the Q Sandbox, there is, if you go to the more details, there is a link at the end, which is actually the running application. So what I did was we are going to use a loan amount, the repayment terms, the installment, the grade of the loan, whether you own or rent a home, what's your annual income. Given all this information, I would love to use one of these machine learning algorithms and then predict the interest rate for this particular loan. So this tool has leveraged past loan data, looked at all the interest rates which people have gotten for various profiles, and has built the best possible model for factoring in. If you provide new information, it's going to come up with the expected interest rate based on these three algorithm choices. So that's kind of the end result of the whole effort I've shown you. Now, how do we actually go about building it? So for the technically savvy and for the people who want to kind of understand the code, if you go into the marketplace, once you're registered based on the code and the information I sent you by email, if you click on Run on Q Sandbox, what's going to happen is you're going to get into your project. So you're going to run this project, and we are running everything on Amazon. So basically what happens is we are setting up an instance on the cloud, and you have your own instance. And when you go in there, you're going to see an interface which looks like this. Give me 1 second. It's refreshing. And then so you're going to see this green button. And when you click on this green button, what's happening now is we are launching what's called as a Jupyter Notebook. So this is basically code written in Python. And when you get into the project directory, I'm going to show you a couple of Jupyter Notebooks. So the first thing we did was we explored the data. And in the context of exploration of the data, we wanted to understand, if I downloaded the data from the Lending Club website, how does it look? So I've written some Python code. If you do not know Python, do not worry. Just focus on like the end results or some of the things we're going to go through. Basically, what I'm saying is, in the context of the case study, I've provided a couple of links in here, which will basically give you some of the summaries of what I've done. If you're interested in the code, you can follow along. If you're just interested in the final outcomes, you can just follow along the case studies here. So here, as I said, as I told you before, so you could have some numerical data and some categorical data. And then you can understand the relationship between various variables by doing some plots. And then you can understand the various categorical variables, what is the term of the loan, the employment length, what is the verification status, where are these people residing. You can also look at the distribution of the kinds of loan amounts people are asking. You can also look at the annual income of various people, and you can try and understand the nature of the various reasons why people are wanting to get loans, and where are they coming from, the different states in the United States. So you can slice and dice the data and understand the data. That's what we did in the beginning. And then what we did was we built out models. And here, the goal was to predict the interest rate, providing, once you understand, what's your annual income, whether you own or rent, what's the purpose of the loan. I want to build a predictor for loans. So basically what we did was we took that data set and we wanted to evaluate what's called as the mean absolute percentage error, which is what I showed you in here. So the goal was to calculate O metric. So here I'm using the mean absolute percentage error. So what we did was we created a function to calculate the mean absolute percentage error and used three different models. One was linear regression, one was a random forest model, and another one was a neural network model. So once we compared the model, we basically summarized the three results and found out that the linear regression model has an 18.68 error rate. The random forest model was much better. The error was much lower at only 5.85. And the neural network had a 6.67% error rate. So amongst the three models, if I have a choice, if I just wanted to get a model which gives me the best or the least error rate, I can just go ahead and deploy a random forest. But now you had to start thinking about, well, will you just look at the error rate, or you have to think about other things like interpretability and stuff like that? Then people may say, well, let me choose a simplistic model which gives me more information on the attribution of each one of these features to the final outcome, and I may choose linear regression to start out with. So depending on where your organization is and what kind of parameters you look for making decisions, you can choose one of these. And the application which I demonstrated basically uses all these three models. So I've kind of incorporated all these three models when we have deployed this. Just to give you a perspective on what modelers typically do, it's a little bit advanced. We don't have time to cover the whole thing, but the point here is they do what's called as hyperparameter tuning. So which is figuring out which are the hyperparameters which could potentially be tuned to help you make better decisions in the context of the model. So when you're trying out various models, the models give you the option of choosing various parameters for the models. You could basically specify various constraints and constants. And the point here is you can fine tune some of these constants you're passing in by using either a grid method or some of the other AutoML techniques which are out there to figure out your best possible option when you're building out the models. So that's an exercise typically data scientists and machine learning professionals go through once they think about honing a particular model for the purpose at hand. And then there are also other enhanced techniques, which unfortunately we don't have time to talk about today. But there are techniques like TPOT, H2O, AutoScaler. I've given you the code if you want to try it out, which typically help you do what is called as automatic machine learning. And companies like DataRobot or Microsoft has an AutoML framework, basically lets you choose various algorithms, and then they fine tune various hyperparameters and gives you the results. So if you just take the same problem statement, as I mentioned, if I was doing manual error rates, calculation of manual tuning of my algorithm, I was able to get to like 18, 5, and 6, as I showed you before. Had I used some of the AutoML techniques, I could have actually reduced the error much lower, much further. So there are techniques which could be used for fine-tuning some of these models. So the summary here is you can basically use Python or any other programming language to write out your models, test it out, and then you can deploy it in a production setting so that you can make that application available and accessible for end users. So that's a little bit about the case study I had. I know we are running out of time, so I want to give a few minutes for Q&A. But thanks so much for making time for this quick 1-hour masterclass. If you like to learn more, we are partnered with the CFA San Francisco Society, and we are offering a 4-week online course, which starts in October. It's going to be 4 weeks in a live stream mode. Each session is going to be 3 hours long. There's going to be a lab at the end of each session, and it's going to be done over 4 weeks. It's going to be 4 Fridays. So you can sign up at the CFA San Francisco website. We are also doing a one-day masterclass, which is an extended version of what we talked about, but going through each one of these modules in a much thorough way. That's happening on August 12th, and that's going to be in New York. Both these classes are available in a live stream mode. We are going to be streaming it in the New York one. We'll send out the details once you register. So if you're interested, please feel free to register there. Both these links are available in the slide deck. So if you go to the Q Sandbox site, the link I sent you, at the end of the slides, you have the links. You can go and register if you want to.